Okay. Can you hear? Yeah. Okay. All right. Welcome to another BIMSA member seminar. So we are thinking together with co-organizers due to the many conferences that are coming up. Probably we are going to be getting close to the end of the BIMSA seminars for this academic year. But maybe we have a few more. Um, but what was it? Question? And okay, in any case, it's a pleasure to have another BIMSA professor, Kazuyuki Tanaka, our famous mathematical magician, with us today. We're going to talk about mathematical logic, unifications, and diversity.
Thank you for kind introduction, and thank everyone for coming to my talk. My name is Kazuyuki Tanaka, and I officially belong to research group of artificial intelligence and machine learning. But more specifically, my research direction is mathematical logic. And in this direction, we have 4 members working on mathematical logic. I and Wenjian Li and Keisuke Yoshii, Kai Ryo. So here is today's menu. Yeah, and main part is part 4, and shadings problem to model checking. So this is the most important part. And after this, 5 and 6 my own research, but probably not much time to explain this part in detail. Now, mathematical logic is preferably called just logic because its diversified aspects towards non-purely mathematical subjects such as AI. About half a century ago, mathematical logic mainly consists of 4 big subfields: model theory, proof theory, set theory, recursion theory. But nowadays, the boundaries are blurred and many new directions have emerged. And furthermore, many recent important topics span multiple areas. Typical examples are determinacy of infinite games and the program of reverse mathematics, which I will explain in this talk. Okay. Mathematical logic has 2 aspects from the beginning. One is a mathematical study of logic. Okay. The other one is a logical study of mathematics. And mathematical study of logic maybe begin with Boole. He formulated Aristotle's logic mathematically. Then Frege extended Boole's logic to predicate logic, including quantifiers. On the other hand, logic of mathematics, logical study of mathematics, begin with maybe Cantor and Dedekind, and maybe more, Bolzano, Cauchy, Weierstrass, there are many, but particularly Cantor and Dedekind are important figure, and they studied real numbers and natural numbers, and they established, it's not easy to control, set theory. Okay? And then in the beginning of the 20th century, Bertrand Russell integrated all of these subjects in type theory. But his aspects, his attempts was too large to be complete. Yeah. Then Hilbert extract just the first order logic and the second order logic from type theory. Then Hilbert coined foundations of mathematics. Right? Continuum hypothesis is a leading problem in mathematical logic. Cantor proved 1874 that the real numbers are not not countable. Then 3 years later, he put forth a conjecture called continuum hypothesis that any uncountable set of reals has a cardinality of the continuum. So there's no intermediate cardinality between countable cardinality of countable infinite and the cardinality of the continuum. The cardinality of the continuum is Aleph1. That means just after the countable infinite. That is Aleph0. So continuum hypothesis is I can't control well. The hypothesis said that the continuum is Aleph1. This was the first problem of Hilbert's 23 problems, which still remains unsettled. But recently, Aspero and Sindra provided a stronger rationale for the negation of CH, that is, continuum is Aleph2. And then they received the Frontier Science Award of ICDS last year. This is not settled. Just they provided stronger rationale. That means that there are several axioms or several hypotheses are known to derive negation of continuum hypothesis. Extra axiom beyond the usual set theory, the extra hypothesis are needed to prove negation of CH. Okay, that extra hypothesis, there are several hypotheses to derive the continuum is alpha 2. Okay, but I didn't say that. I didn't say it's settled. Just they provided stronger rationale. That is not solution.
No, but why do you say it's unsettled? It seems to be settled by Paul, Gödel and Paul Cohen. In what sense it's not? They showed it's independent. So
independent, but to find some plausible hypothesis to get negation of CH.
Well, you can make a hypothesis that implies hypothesis that don't imply negation. Both are equally valid. In what sense it seems to be settled by Paul Cohen. So I don't understand the statement that it's
no. Just they proves CH is independent, but many people thinking about stronger hypothesis, large cardinal hypothesis, and some hypothesis of combinatorics. They are independent. All of them are independent beyond the set theory.
Yeah.
And some of them implies negation of CH. That situation is very how to say, mm, set series satisfy this situation. Probably non-set series like me, I can't understand. I can't understand well, but some conjecture or hypothesis implies not CH. So they study the relation of hypothesis. And these two relations are consistent, then not CH looks like true. I'm sorry, I can't explain
Yeah, thank you.
it. Then Hilbert himself to settle this problem by reducing it to Einstein's problem. It is also called decision problem of first order logic. But because set theory itself is formulated in first order logic, that's the point. Set theory is first order theory. So if we know first order logic completely, then set problem of set theory should be solved. So expected, but actually, first order logic is not decidable. But first of all, what is first order logic? First order logic is the logic just treat these quantifiers only range over elements of object. Just for all elements of the given structure, not talking about subsets or in general set, just elements of structures. So sometimes first order logic is called elementary logic. And of course, it may treat propositional connectives and mathematical symbols. Then Hilbert Ackermann's textbook, Grundsicher, in 1928, they said the decision problem is solved when we know a procedure that allows for any given logical expression to decide by finitely many operations its validity or satisfiability. So the decision problem is to find the algorithm by which given first order formula, essentially first order formula is valid or satisfiable. Valid means it is true in any structure. Satisfiability means there are some structure exists satisfy that formula. Then they also said that decision problem must be considered the main problem of mathematical logic. They wrote so. Then soon after that, Pressburger proved that first order theory of natural number with just addition, no other operation, just addition, is decidable. And Scoren proved natural number with multiplication, only multiplication is decidable. Then Ramsey introduced a theory about the partitions to deal with a simple case of the enshading problem. This problem is about pure logic. Okay, these two results is about number theory, but pure logically valid or satisfiable. That is decidable for very special form of formula. Then his result itself is not so important, but his proof technique is now called the Ramsey's theorem, and that is used in many branches of mathematics. Okay, Ramsey's theory first appeared in his paper on the problem of formal logic. Then Gödel proved that any first or even higher order, first order theory, including arithmetic, has an undecidable proposition. Then, in particular, first order theory of natural number with addition and multiplication both is decidable. This is a famous paper of his incompleteness theorem. But essentially, he talking about undecidability problem. Then 5 years later, Church and Turing independently proved that the validity or satisfiability of pure first order logic is not decidable. Yeah, particularly the Turing's paper is very famous. It's on computable numbers with application to the Entscheidungs problem. In this problem, he defined the so-called Turing machine to show something is not computable. And some problem cannot be decided. Okay. On the other hand, Tarski proved that the first order theory of real closed field is decidable. Also, the decidability of real exponential field, just the field with exponential function. The decidability, it is still unknown. And he also proved that the elementary Euclidean geometry is decidable. So now, decidability problem is, the decidability problem becomes a classification problem. The theory is decidable or non-decidable, just classify the theories into two categories. Meanwhile, mathematical theories can be developed as a first order theory, but first order is not so powerful to describe some structures. Many simple properties of structures cannot be described by first order formula. For instance, a set has even number of elements. Finite set has even number of elements, or a graph is connected. These concepts cannot be described by first order. Okay. The first order just has a variable over elements. Then also second order logic are considered. Monadic second order logic, MSO, is a first order plus quantifier over subsets of the structure, this, and the unary predicate of the structure. Then graph is connected can be expressed as a connected component is a whole graph. So there is a, for all x, this, sorry, run over subset of the structure or maybe subgraph. So we can talk about certain connected component, like this way. So connected component is a whole graph. So we can describe the graph is connected. in second order logic is easy to handle. Yeah, first order with many variable relation, NRE relations, and functions. This is just one variable predicate. This has two or more variable and the function. With these quantifiers, for instance, parity, add or even of set can be defined by a certain function, one-to-one function. You can compare the cardinality of set. So you can define the parity. So to describe structure, these logic are useful. Then for this logic, still some theory are decidable. First, 1960, Buch proved that monadic second order theory of natural number with just successor function, only +1 is given. Then, but this, I don't know why it's so difficult to control. This only successor function, but because of the second order variable, you can define the addition. So monadic second order of natural number with successor includes first order theory of natural number with multiple, I'm sorry, that's first order theory of addition. Okay. So Buch result includes Pressburger's result. Pressburger arithmetic is embedded in this theory. Okay, he proved this by using omega automata, which yeah. Okay, first, this is the picture of a usual finite automaton. Finite automaton read finite sequence of symbols from left to right. Then when it reads the last symbol, the internal state is final accepting state. Then automaton accepts this finite sequence. Automaton has several good property, but particularly the emptiness problem of language accepted by automata is decidable. And several decision problems are solved for automata. And Buch extended that kind of idea to infinite tape automaton. Then he proved that MSO with +1 is decidable. That system is called S1S, second order, actually monadic second order with one successor. Then Rabin extend this to binary sequence. Monadic second order of binary sequence with two kinds of successor functions, adding 0 at the end of the sequence and also adding 1 at the end of the sequence. Monadic theory of such a structure called S2S is decidable, and Rabin used tree automata. He invented tree automata, and his argument is so complicated. Then later, Greenwich-Harrington improved the proof, simplify the proof with the help of infinite games. Now, three automata and the S2S and the infinite games are connected. By the way, Harrington is my thesis advisor. And also, difficult to control. Another proof by Nowinski use model view calculus. That is what I will explain soon.
That's your question.
Yeah.
So in the previous slide,
Yeah.
I'm trying to understand what these means, these sentences. So am I right that as kind of a logical system is decidable if basically there is a way, like if I make some proposition, then you would tell me that there is a way to relate this to a set of logical rules based on which you can define if it is wrong or right. Is this decidability? Is this the meaning of decidability of a system?
In particular, which part do you?
Well, first I need to understand decidability. Then if I understand decidability.
Okay. Decidability is the method is anything. There's like some machine to check whether it is provable or not, or true.
Yes. So comparisons with certain set of. Now, my question: why is it that decidability can be related to something like automata? Because
automata.
Yeah. Isn't it automata is basically just a set of states which can be parameterized by time steps? Isn't that what automata is?
Automata, yes, yes.
How can it determine decidability of the system?
First, automaton has no just a finite machine.
Right, okay? It's just a finite
memory.
That's it.
So yes. So just looking at the definition of automata, you can definition means the function of automata. You can decide that automaton accepts some sequence or not.
Okay, if it accepts a sequence in which certain state appears infinitely many times, then that system is decidable.
This is now just a different. You're talking about omega automata.
Yeah,
okay? Omega automata is infinite tapes. But accepting condition is only some state appear infinite many times. And the automata itself is finite machine, so infinite many times appear, but actually it is periodic. So it's possible to decide certain sequence is accepted or not.
Nice. So repetition basically implies decidability.
Yes.
Periodicity implies.
Yes. That is the point. Yeah. Then this is some idea of Levin's tree. Why he used tree. But before Levin, there is a proof of theorem of Skolem about multiplication. The multiplication can be represented as a tree like this by using a prime factorization. Just to use 2 to the 3 2 cubed is just 1, 1, 1, 0. This is 0. Okay. This, how to say, this is the highest degree, highest. So this is actually 1, 1, or this is 1, 1, 0 means 6, and this is 1, 1 makes 3, and so represent a number like this 3, and multiplication of them is just addition by pathwise. So just Rabin's argument includes Skolem's proof. It's just I say that this is much more complicated, but yeah, expanding a tree, then situation gets somewhat simpler. Then this is a main point. Enshrining's problem to model checking. Enshrining's problem is the following: fix an object M or theory T. M is like a field of real numbers or some natural number. It's a fixed object. They input the formula P, then decide P holds or not. Okay, so, but model checking, input model and formula, then decide P holds in M or not. So like model is this case is a state transition graph. Then state transition graph is just a directed graph, and the formula like so it is connected. Well, it includes a loop. Such a formula is given, then graph and the formula given, then decide that the formula holds in the graph. Yes.
Can I ask, how
Yes.
do you read off this graph? How do you, so this previous slide.
A previous slide.
How do you read it off?
Just binary representation to exponents.
Ah, and then the product is, yeah, okay. And the product sense. Okay, yeah. Thanks.
Then yeah, model checking is really useful, and classical verifier, it's called SMV, symbolic model verifier, is a widely used model checking tool developed at Carnegie Mellon that analyze finite state systems by using temporal logic, CTL. CTL is computation tree logic. CTL use temporal logic is actually propositional logic with some extra operator. Then it has an operator express next step or next node something holds, or eventually something holds, or path quantifier for all paths, and actually many other operators are provided. And CTL has many variations, and also SMV. This is the oldest version. New version is a new SMV, or SMV2 is also developed. But essentially, they are based on temporal logic. And temporal logic is a kind of modal logic. Modal logic is, in the general name, for propositional logic and modal operator. Like this. And CTL, this CTL and its variation can be easily transformed into modal logic with fixed point operator. It's called the modal mu calculus. Fixed point operator, mu. Then
you gave examples of the first order, the second order. Is this temporal related to those?
Yeah, I explained that modal logic is a modal logic or temporal logic with a simple quantifier is embedded in first order. Then with mu operator included monadic second order. But first order monadic second order are too strong to decide the validity of the formula. Then say modal logic is propositional logic with the modal operator, and this operator means for all next step, if you consider on the state transition graph, then next node p holds, all next node p holds, and diamond p is at least one next step p holds. So this is easily expressed by first order. Just at node S, box P holds means all T, S, there's a H from S to T, then at T, P holds. In this way, you can translate modal logic to first order logic. Also, mu calculus is just difficult to explain that this has a fixed point operator, greatest fixed point and the least fixed point. And fixed point can be expressed by monadic second order. Then monadic second order is powerful. And then, see what is it? It's okay. Then the relation between modal mu calculus and the infinite game, the equivalence between modal mu calculus and tree automata over just binary trees, they are essentially shown, they are equivalent. Okay, modal mu calculus description power of modal mu calculus and tree automata are equivalent over binary trees. But other cases, not I claim that over binary trees, they are equivalent. And evaluation of modal mu calculus also works on any graphs. The evaluation of modal mu calculus is actually, it's not easy to define, but usually we define the truth false of modal mu calculus on the graph by using the idea of infinite game. Just the player plays sub-formula of given modal mu calculus. They choose a correct path. Then, so in using infinite, the game may not finish, so it is an infinite game. Particularly using mu calculus, some part appeared infinite many times. Then determinacy of such a game can be expressed by monadic second order. Determinacy is expressed by second order, monadic second order S to S, and decidability of monadic mu calculus is shown from Rabin's theorem. Also, Rabin's theorem can be proved from decidability of monadic mu calculus. Then some important results on variations of modern mu calculus have been obtained by comparing the determinacy hierarchy of Gale-Stewart game. Here's a Gale-Stewart game, and two players, they select elements from given set A, and they play alternatively, and they make an infinite sequence. That infinite sequence belongs to X. Then player one wins this game. The game is defined by subset of this product space. Then game X is determined if either one or two player has a winning strategy. Then it is known that yeah, that's the most important thing is Martin showed that the Borel sets are determined. Then well, actually, this point is important. Decidability tree automata, Greenwich-Harrington introduced a forgetful game that is equivalent to parity game. The parity game is a game with a winning condition in the Boolean combination of F sigma set. Sorry, too technical. Meanwhile, there's a study of reverse mathematics. And they classified mathematical theorems into mainly 5 systems, depending on how this is a system of second order arithmetic. Second order arithmetic is first order arithmetic with set existence axiom. Then RCA is just a computable set or recursive set exists. And WKL is for weak Koenig's number that and arithmetical comprehension, etc. And many mathematical theorems are classified in these categories, but determinacy, even open determinacy, is this level. The next level, open and closed determinacy, is pi 1 CA. Then sorry, this is more almost finite. And I and people working with me introduce several set existence axiom to classify games upper sigma 01 to delta 03, and also above delta 03, several people classify the games. Now these are mainly my result. And this is almost, so we studying reverse mathematics of infinite games. And for weak system, WK node, we also interested in the study on non-standard model of WK node. Yeah, and also I'm working on the game trees and the evaluation cost. We investigate the form of distribution of the truth assignment of a weighted Boolean tree when it achieves the equilibrium among the independent distribution. Yeah, these are three main themes of my research. Thank you. Thank you for your attention.
Okay, questions?
This is a picture of people. Yeah, orbit express the equivalence.
Yes.
So would you say, so the zero, would you say that the classification means that the Cantor-Bendixson theorem should be viewed as a deeper result than the Losing separation theorem? Because, you know, ordinary mathematicians, we don't normally think that way.
I don't think so. Because even something proved in a very weak system, but still it has a deep meaning. In RCA nodes, there's many important theorems.
I see. So there can be high complexity of proof at a kind of lower logical level.
In the sense, yes, but we can measure everything by such measure. Yeah, that we get one measure to look at all mathematics, but it's not a universal measure.
Thank you.
Thank you.
More questions?
Thank you so much for the talk. I'm just curious, like, is there any relations with Tarski's decidability of real exponential fields with the continuum hypothesis?
I think there's no relation. I've never heard about such. It's just exponential field, decidability of exponential field related to Chaniol conjecture.
Yeah, thank you.
More questions? So I'm curious, is there any effort to model these with geometry? For instance, this modal calculus that you were mentioning, it very much looks like defining an algebra. Are people doing this, or is this?
I don't know. Probably not many. Maybe some people working. I'm sorry, I don't know.
Like, for instance, if two things are formulas, then their sum is a formula. Some difference is a formula. This and that is like a product structure. That's a formula. It's very similar to defining an algebra with all the properties of an algebra. Has this ever been done? No. There is some attempt.
Thank you.
Any more questions? Well, if not, let's thank Kazuyuki again.
Thank you.